Hi, I am FutureiAI. We are going to learn tensorboard today. Tensorboard is an open-source visualization tool developed by Google, which displays the changes of the model during the training process in a graphical way. It has rich features and is widely used. The content of the subsequent explanation in this video is a guide for the use of the model trainer and will not involve other functions, such as algorithm design and implementation. We can click the Training Process button on the model page to open the tensorboard page. Since the model training has just started, there are no charts yet. We can click on the last module, which is the time service, to enter this page. And then on the left side, we can see the past training lists are divided into different colors. After checking all of them, we can see the training curves of each model on the same graph for comparison. We can also retain only one training process to see the changes in the model data during this training process in detail. Then we look at the other columns of data on the page. This version of tensorboard provides for main types of data. One is the scalars module, which is a scalar used to display various statistical data in charts. The image module can display various images recorded during the training process. The text module can display various text records from the training process. The graph module can display the computational graph of the algorithm. We focus here on the features for model training, that is, the scalars module. First, you should look at the loss, which is the most important data in the scalar module. Loss can be understood as the average error, reflecting the difference between the model's current performance and the annotations in the dataset. The horizontal axis of this chart is the number of iterations, and going through the entire dataset once is called one iteration. The vertical axis is the actual loss value. The default training is for 100 iterations. This chart shows the process of the average error, gradually decreasing as the number of iterations increases. For example, this chart shows the process of loss change after 30 iterations. And this chart shows the process of loss change after all 100 iterations are completed. There are two types of loss. Training loss is the average error calculated for the training data set, and val loss is the average error calculated for the test data set. In the training loss, there are three categories. CLS is an abbreviation for class, representing whether the correct classification has been made. Box loss represents whether the correct location has been found. OBJ is an abbreviation for object, representing whether the object has been detected. It is a comprehensive result of both class loss and box loss. If the business scenario is more concerned with correct classification, then we focus on the class loss chart. If the business scenario is more concerned with the location of the object, then we focus on the box loss chart. Taking the box loss chart here as an example. The loss has been steadily decreasing over 100 iterations, indicating that the training was successful. And increasing the number of iterations may further improve the performance of localization. Looking at the class loss chart here, the loss has been steadily decreasing over 100 iterations, but the slope is getting smaller and approaching zero, which indicates that increasing the number of iterations may not significantly improve the classification performance. It may require more data to further enhance performance. Trainers need to find the appropriate number of iterations based on the difficulty of the actual scenario and the quality of the dataset. When the quality of the test set is reliable and the number of iterations is sufficient, validation loss, val loss, and training loss, train loss can be used together. Following are some general training rules. I won't talk them in detail here. Everyone should read the screen to understand them well. Then let's look at this set of metric charts. This represents the model's accuracy as it changes with the number of iterations. MAP stands for the mean average precision across multiple classes, where the area of overlap between the box and the annotation that exceeds 50% is considered as a score. The accuracy for each class is calculated, and finally, the average of all class accuracies is taken. The second map, 0.95, is also the mean average precision across multiple classes, but the overlap between the box and the annotation must exceed 95% of the area to be considered as a score. The last two are the standard precision and recall rates, which I won't elaborate on. This set of charts is relatively less important, and the role of map is similar to that of validation loss. This data might serve as a more intuitive and understandable metric for users, but in fact, this value is greatly influenced by the quality of the test set itself and cannot be compared across different models. It can only be used to compare whether there has been an improvement within the same model. The value of loss, on the other hand, has better comparability between different models, so trainers should pay more attention to the changes and values of the loss metrics. XLR represents the learning rate. If you are not concerned with the details of the algorithm, you can skip this part of the explanation. Adjusting the learning rate can help the network converge quickly. Generally, starting with a larger learning rate and then reducing it tends to yield the best overall results. However, what the best initial value is depends on the chosen algorithm and the characteristics of the dataset itself. This chart can reflect the specific changes in the learning rate during the training process, allowing for corresponding adjustments. LR0, LR1, and LR2 represent three sets of learning rate-related parameters, corresponding to the shallow, middle, and deep layers of this model. Since our current algorithm uses the warm-up technique, it will automatically start with a smaller learning rate, find the appropriate maximum learning rate, and then gradually decrease. Therefore, you can see that the learning rates of the first two sets increase and then decrease, indicating that the adaptive effect is very good. The last set of LR corresponds to the learning rate that starts large and then decreases, as the deep layer training did not use the warm-off technique, so the chart's performance is also as expected. The above is the knowledge related to tensorboard that model trainers need to understand. For those interested in other features, you can visit the TensorFlow official website to find more information. Alright, we finally finished this lesson. The content is a bit much, so I hope everyone will review it well.